In this lesson, as part of our curve sketching unit, we're going to be taking a look at what are known as critical points and the first derivative test. Now, the first derivative has played an important part in a lot of what we've done in the calculus course overall. And that is because we know that if we take the first derivative and we set it equal to 0, whatever value where the first derivative is equal to 0, so I'm going to call that value a, that means that x equal a, or a itself, is called a critical value. And the point on the original function that corresponds to that, so in this case, the a value would be the x coordinate and f of a would be the y coordinate, that is known as a critical point. So the critical value is just the x coordinate. So that's the x coordinate only. And when we combine those to find an actual point using x and y, that's known as a critical point. These critical points, when we find them, are generally points that we're very interested in. These critical points can be a maximum. That is where the slope is equal to 0, but it's also, and the reason I'm going to kind of give you a different definition of this is because the slope equal to 0 is not a completely well-defined way of finding a maximum or a minimum, and we're going to be exploring that as well. So a better way to describe a maximum is when your slope is changing from positive to negative. And another way to say that would be also that the function goes from increasing to decreasing. Same idea, because an increasing function has a positive slope, a decreasing function has a negative slope. A minimum, on the other hand, we have a slope changing from negative to positive, which means the function goes from decreasing to increasing. And then we can have what's known as a point of inflection, which is sometimes shortened to a POI, just because point of inflection is a lot to write out. And in a point of inflection, the trend in the slope continues. And so an example of a point of inflection, just to sketch it very roughly, we might have a slope that is positive and then it levels out and then it goes positive again. So as you can see, at some point in time we pass through a section where the slope was equal to 0. So that's a critical point. But this is not a maximum or a minimum. What we have here, this is known as a point of inflection, because here we had positive slopes, here we have positive slopes. Now, what if we find this value x equal a, but we're not able to find a value where it's equal to 0? What if we find out that there are some values of a where the derivative is undefined? Then x equal a is a critical value. It's, once again, this is a critical value. But the meaning of this critical value can be different depending on how does that critical value tie into the original function. So for example, we might find a critical value that was a vertical asymptote on the original function. And if that's the case, it doesn't form a critical point. Yes, it's a critical value, but it's not a critical point, it's just a vertical asymptote. If it, on the other hand, occurs at a maximum or a minimum on the original function, and yet strangely enough it's undefined in the derivative, this is a critical point, and it's a very special kind of critical point. It's called a cusp, and we're going to take a look at that type of critical point as part of this lesson. Okay, so let's go ahead into an exercise. Consider the function defined by f of x equals x to the 4 minus 3x cubed. So simple polynomial, its domain is all values of x, and it is differentiable everywhere. First of all, find all intercepts. So that means find all x-intercepts and find all y-intercepts. So to find all of my, let's start with the y-intercept, because for the y-intercept, all I need to do is find out what is f of 0. And in this case, I end up with 0 to the power 4 minus 3 times 0 cubed, which of course works out to be 0. So I have a y-intercept at 0, 0 at the origin. For my x-intercepts, I set f of x equal to 0. So I get x to the 4 minus 3x cubed equal to 0. I have a common factor of x cubed, and then I have x minus 4, sorry, x minus 3. I have x minus 3 remaining. And so that gives me, the solution to this is that x is equal to 0 or x is equal to 3. And I just want to point out here that this actually is x equal to 0 3 times because this is x cubed. And what I mean by saying 3 times is that this is what's known as a triple root. And that's something that you would have discussed in your advanced functions course, the idea of a linear root, which is what this one is. So this one is a linear root. You can have a double root, which is quadratic. You can have a triple root, which is cubic. And that's going to have a bearing on our graph. Now, the other thing I've been asked to do is, let me just partition this. So for part B, I have been asked to find critical points. So for that, I'm going to need the derivative. So I'm going to find f prime of x, which is 4x cubed minus 9x squared. Then I'm going to set f prime of x equal to 0. So I get 0 equals, and I'm going to go ahead and start to factor this all in one step. I see a common factor of x squared, and then what remains is a 4x minus 9. And so what that gives me here is x equals 0 or 4x minus 9 equals 0, which is the same as x equals 9 over 4. And so in doing that, what I have found here, these are critical values. We have found values where the derivative, where the first derivative, because this is part of the first derivative test, we're testing where is the first derivative equal to 0. So now that we have found these critical values, we could identify all critical points. So it's not enough to just find critical values. We have to find the critical points that go along with these. So the way that we do that is we just substitute these as x coordinates into our original function. So we are going to now find for x equals 0, what is f of 0? Well, we've actually already found out f of 0. It was one of our intercepts. F of 0 is equal to 0. So that's straightforward enough. What about this one? What about f of 9 over 4? Well, there's a little bit more involved there. That's going to be 9 over 4 to the power 4 minus 3 times 9 over 4 to the power 3. And notice I'm working off of the original function. I used the first derivative to find these critical values. I'm now subbing these critical values into the original function to come up with a numeric value that goes along with them. And so when I go ahead and I work this out, I end up with 6561 over 256 minus 3 times 729 over 64. And with a little bit of simplification and common denominators, because I prefer exact values whenever possible, I end up with negative that doesn't look right. Oh yes, yeah, that does look right actually, because of the common denominator here, 256 versus 64. It actually ends up, the negative one actually ends up dominating, and I end up with negative 2187 over 256. Now this one, that just means I have a critical point. Critical point number 1 is at 0, 0. And from this one, I have critical point number 2 is at, the x coordinate is 9 over 4. The y coordinate is negative 2187 over 256. So those are my two critical points. Now, once we get to sketching, obviously this is very awkward to use. We're probably going to have to convert that to a number if we want to do anything with it as a number. But right now it's an exact value, and I'm perfectly happy with that. Okay, the next part is, here is our function. Classify those critical points using an increase-decrease table, or we've talked about this as an interval table. So to classify those critical points, what I need to do, here's f of x in its factored form. We found out that we had factors or solutions at x equals 0. So if I put 0 equals here and 9 over 4, so I need 3 intervals that I need to consider. So let's, for example, choose something to the left of 0, so negative 1. To the right of 0, 1 will work there. And to the right of 9 over 4, so 1 is between here. And so I would choose, well, I could choose 3, but I could also go further. I could choose 5. To figure out my interval, what I need to do is I need to look at my factors, which are x squared and 4x minus 9. X squared, no matter what value I put in here, x squared is always going to be positive. And if you notice little things like that, you can go ahead and you can fill them in. 4x minus 9, if I put a negative value in there for x, this works out to be negative. If I put 1 in here for x, 4 minus 9, that's still negative. And if I put 5 in here for x, 4 times 5 is 20 minus 9, that's positive. So what kind of results are we going to get for this? Positive times a negative gives me a negative, and that means that this is decreasing. The derivative is negative, so this is a decreasing portion of the graph. A positive times negative is negative, that means this is decreasing. And a positive times positive is positive, that means it is increasing. And the other part I haven't filled in yet is just defining this interval. You don't have to do this as part of the interval table, but you're going to have to do it eventually. So where is this particular interval of decrease is going to be from negative infinity up to 0. This interval is going to go from 0 to 9 over 4. And this interval is going to go from 9 over 4 to infinity. So classify critical points using an increase-decrease table. What that means is I've defined where are these things increasing and decreasing, and I'm going to use them to classify. What do I mean by classify? That means tell me, do I have a maximum or a minimum? That's essentially what we're talking about. Or do I have a point of inflection? So if we take a look at this, what do we have happening here? We have, so this was positive all the way across. So at 0, we have decreasing. So that means that the function is going like that. Here we have decreasing. That means the function is also doing something like that. And here we have increasing, which means the function is doing something like that. So if we imagine those, and let me just go back, I just want to refresh your memory about our definitions. A critical point can be a maximum, which means the slope is changing from positive to negative. That would be increasing to decreasing. A minimum is decreasing to increasing, and a point of inflection is the trend in the slope continues. So, to classify this, what do I have here? Here I have decreasing, and here I still have decreasing, which means from here to here, my trend continues, and that means I have a point of inflection. That is x equals 0, is a point of inflection. Or sorry, not x equals 0. The critical value occurs at a point of inflection, which is actually the point of inflection is 0, 0. So the point of inflection, the way I should say this is I have a point of inflection at x equals 0, but the actual point of inflection is the point 0, 0. Here, I'm going from decreasing to increasing. From decreasing to increasing, you can even see it in the motion I'm making there. That's going to be a minimum. So here, I have a minimum, and I don't know if it's a local or an absolute, so I'm just going to say I have a local minimum at, and in this case it was 9 over 4, and then the other value was negative, and what was that? 2187 over 256. 2187 over 256. Okay, so now I have identified, let's ignore that message. Now I have identified a point of inflection and I've identified a local minimum. And I say to sketch this. So I know that here at 0, 0, I had an x and y intercept. And I also know that if we go all the way back to that first slide, not the first slide of the problem, I also had an x-intercept at 3. So an x-intercept at 1, 2, 3. All right, so now I know the graph goes through those 2 points. And I also know that it goes through here as a triple root, and I know it goes through here as a linear root or a single root. Now, what do some of these other things tell me? I know I have a local minimum at 9 over 4. Now, I chose my scale pretty carefully in advance here. You can see I've broken up each of my, if this is 1, 2, 3, 4, I've broken this up into 4 pieces. So 9 over 4 would be 1, 2, 3, 4, 5, 6, 7, 8, 9 over 4. So along this line is going to be my minimum. Now, because I'm only doing a sketch, I'm not going to worry about my vertical scale, and that's quite often when you're asked to do a sketch. If anything, you're going to concern yourself with your horizontal scale, but the vertical scale is kind of irrelevant. I know that from 9 over 4, I'm increasing. From 9 over 4 to infinity, I'm increasing. So that means from this point through that x-intercept, I'm going up and up and up. I also know that over here I've got a triple root and a point of inflection. So the way that's going to look is it's going to go here and then go flat and then go up again. And so we end up with, so here I'm just going to highlight it. So right here I have my point of inflection. Here I have my minimum, and we can actually see from this graph now that it actually is my absolute minimum. And I've got a 0 here and a 0 here at that point of inflection. So we're getting into more sophisticated graphs, and we're using the tools of calculus to help us be able to sketch them in a fairly accurate manner. And I've got one that I've done with technology here. Here is the actual graph using GeoGebra. And as you can see, that's a pretty good match. There is, right there is 9 over 4, and that's what gave me my local minimum. Here you can see that point of inflection. For the next exercise, you can probably see from looking at the function, it does look a little bit different than what we looked at before. The structure of it is quite a bit more complicated, and that's going to introduce some new features when it comes to this whole idea of the first derivative test. So the first thing I'm going to do here is I'm actually going to rewrite this in a form that's a little bit friendlier, a little bit easier to deal with. So I've got x plus 3 all squared, and I've got the fifth root of that, which is the same thing as saying it's to the power 1/5. And then I'm going to combine those exponents, and so that's x plus 3, and then I just multiply these together, and so that overall is x plus 3 to the 2/5. And now that I've done that, I can go ahead and start with my first derivative test. So f prime of x is going to be equal to, and I'm going to use the chain rule here. So my exponent of 2/5 comes down out front, x plus 3, and then I subtract 1 from my exponent, and that gives me negative 3/5. And this is a chain rule, so I do have to take the derivative of what's inside the bracket here, but it turns out the derivative of x plus 3 on its own is just 1. So that actually is my derivative. So for my critical values, I'm going to set f prime of x equal to 0. So we're now going to try to find some critical values of this. So we end up with 0 equals, I'm actually going to return this to the form it was in before, in the sense that I've got 2 in the numerator, 5, and then this thing, which is in the denominator, is the fifth root of x plus 3, but because of the derivative we took, it has changed it, and this is now cubed. So I've got 0 equal to this thing. Now typically, what we would do at this point is we would cross multiply. And when I cross, that looks like CCROSS. There, cross multiply. And when I do that, I actually end up, this whole denominator cross multiplies into the 0, becomes 0, and I end up with 0 equals 2. And at that point, I wonder, has something gone terribly wrong? And if you think back far enough, you've seen situations like this before. When you are attempting to solve and you end up with an expression like this, what that actually means is, therefore, we have no solution. So we're not going to find any critical values by solving this equation. But there is one other thing that we also have to consider here, which is, so what this is essentially saying is, it's saying we have no place, there is nowhere is the slope equal to 0. But there is something else I have to consider, which is the fact that by taking the derivative, I have taken this x plus 3, or this fifth root of x plus 3 all squared. It's now in the denominator. And by moving it to the denominator, I have to avoid division by 0. So what that means is we also have to consider that essentially this whole denominator, 5 times the fifth root of x plus 3 all cubed, cannot be equal to 0. But what that really comes down to, the only thing that's going to make this equal to 0 would be if x plus 3 were equal to 0. So we need x to be not equal to negative 3. And what we have here, so we know that x cannot be negative 3 in f prime of x, but f of negative 3, that's the next thing I need you to ask yourself. Let's go back to the original function. But f of negative 3 is the fifth root of negative 3 plus 3 all squared. Negative 3 plus 3 is 0. 0 squared is 0. And the fifth root of 0 is 0. So what this means is that f of negative 3 exists. F prime of negative 3 does not exist. And what that tells us is that there is something interesting happening at x equals negative 3. And this is known as, so now we actually do know, this tells us that x equals negative 3 is a critical value. And since f of negative 3 exists, that means that negative 3, 0 is a critical point. And if we go all the way back to what we started talking about in this lesson, on f of x, this critical value, so here we have the situation. If f prime of a is undefined, then x at a is a critical value. This critical value can occur at a vertical asymptote, which means there's also a vertical asymptote for f of x, but that wasn't the case. We had a value for f of x, and that means that this is actually a local extrema. It's either a maximum or a minimum, and this is known as a cusp. So with this very kind of odd fifth root of something squared that we started with, we have actually found that this is a cusp, which is this new idea of a shape. I've actually shown you this shape before in other graphs, but we've never really talked about what it was. Now, if we were going to finish the analysis of this, what we really should do is we need to test if this is a maximum or a min. So we would test values, basically we would test values of x that approach 3 from the left side, and we would test values of x that approach 3 from the right side. And if we were to substitute those, what we would find is that f of, let's say from the left side, well, that might be, for example, f of 2. And from the right side, we might take a look at f of 4. And if we go ahead and put those in, now I'm not going to worry too much about the numbers here because unfortunately, sorry, I said 3 from, it's negative 3. So actually I should be looking at negative 2 and negative 4. Now it's not going to work out too nicely. Actually, the numbers I've chosen here work out just fine. When I put negative 2 in here instead, I get negative 2 plus 3 is 1. 1 squared is 1. The fifth root of 1 is 1. So that's equal to positive 1. When I put f of negative 4 in here, I get negative 4 plus 3 is negative 1. All squared is positive 1. The fifth root of positive 1 is 1. And so you notice that these values are higher than this value. So therefore, negative 3, 0 is a minimum. So we have a cusp here that is a minimum. But because f prime, if I go up a little bit, f prime of negative 3 does not, I said it does not exist. I think I'd rather say it is undefined. That actually means that the slope is getting infinitely large there. It's like a vertical asymptote. So the slope is approaching a vertical asymptote, even though there's a point there. And so the shape that it takes on in this case, because this one's a minimum, is going to be that. And that's known as a cusp. And I've done a nicer graph to reflect that. So there it is right there at negative 3. And you can even see there looks like there's a little gap there, but there's actually no gap there. It's because even the software itself has a hard time of bringing that all the way down to negative 3, because the slope, as we kind of dive into this cusp, becomes closer and closer to positive infinity and closer to negative infinity, and the GeoGebra software just has a hard time handling that. Okay, so that's it for the first derivative test, and there is some assigned work to keep you entertained as you practice your skills with this.